pleasure to introduce Dr. Tommi Jaakola from MIT. He started his career in theoretical physics at the Helsinki Institute of Technology for a master's degree. Then he went to MIT in the AI lab where he worked with Michael Jordan on machine learning. Then after getting a PhD at MIT, he joined the University of Santa Cruz for a short while for a postdoc with David Hostler. And recently he went back to MIT, where he's now an assistant professor in the AI lab, and where he's continuing work on machine learning, theoretical and experimental aspects of machine learning. And today we'll talk about discriminant classifiers with incomplete data.
Thanks. Okay, so let me start by first acknowledging two co-authors, Marina Mellers at CMU and Tony Jabara, a graduate student at MIT. So the view of discrimination, well, before I actually start, I should say that you should feel free to interrupt me at any point if something is unclear, and just make it interactive. Okay, so the view of discrimination here is quite general, so it covers a lot of ground, and the attempt here is to formulate something general that can actually address problems in all these areas. So standard use of discrimination is in classification or regression. You want to classify documents into categories. You might assign protein sequences to different existing families. You might do single word recognition, and so forth. Now, an extension of that discrimination problem is a problem where we not only have labeled training examples, but a large number of unlabeled examples as well. So, for example, it's typically costly to assign labels to documents, but you have less number of available documents. So if you want to train a effective classifier for document classification, then you better be able to deal with unlabeled examples as well, or exploit whatever information is in the unlabeled examples. Another way where examples or labels can be missing is in the context of anomaly detection, where you have examples from only single class. But you nevertheless want to discriminate examples in that class against a diverse set of other examples that there might be. So you might have examples from a particular person uttering a particular word. You might have examples of certain type of documents, and now you want to go ahead and search for the same type of documents in a large collection. So it's still a discrimination problem, but has a different notion of incompleteness in it. Now, going even further, some of the missing components in discrimination problems could be the features. So, for example, in document classification, certain words are more informative about the category that the document belongs to than others. Okay, and you would want to then base your classification scheme primarily on those discriminative words. Okay, so that's feature selection problem that I will formulate as a discrimination problem and solve feature selection jointly with the classification task. Then there are sort of even generalizations that go basically beyond standard notions of classification and discrimination, which is the problem of structured labels. So each example might have transformations particular to that example. So one example of that is when you have to align your example to, say, model or other things before you can classify it. Okay, and you can view that as a problem where the transformation is hidden. You don't know what the correct transformation is, but you still want to do classification in this setting. So there are lots of discrimination problems, and we would like to solve all of them. So let me first clarify what is a discriminative method based on that description. It would be a method that uses an estimation criterion for parameters, structure, whatever, that closely matches the criterion by which that method will be evaluated subsequently. So if I have a model and I train it with maximum likelihood, so I'm trying to model the density of the examples, not how that model will allow me to classify the examples, then I'm using a different criterion for estimation than for evaluation, and that method would not be discriminative in this sense. Okay, so...
Not necessarily.
Sorry?
Not necessarily.
Not necessarily, but what it says is that there's a mismatch between the criterion, and you better have some other reasons to suspect that doing these two different things lead to the same goal that you're trying to solve.
But you can train both systems, both feature extraction and the models together, and then therefore there's no mismatch.
I'm not claiming that feature selection, there's a mismatch. I'm in fact formulating a feature selection as part of the discrimination task. I'm claiming that standard maximum likelihood estimation of density models, there is a mismatch if you are using those models subsequently to classify examples, not say evaluate how likely they are from that model. Okay, so within that general discriminative formulation, there are several challenges that we have to address in order to make this work. One challenge is effective representation of the examples. So documents are sort of flexible objects, speech signals, certainly protein sequences, and we have to use them in a way that's effective for the discrimination task. And the other other challenge is dealing with this incompleteness of information that can sort of arise from labels, features, missing components, and so forth. And we want to do this, deal with this and exploit examples that have missing components to improve the classification. And we want to do this in sort of a more general way, not solve any single task separately, but have some methodology for solving large number of these problems. Okay, so let's take a couple of examples. Here are two protein sequences of variable length. And if you know nothing about proteins, then it's very hard to classify these examples. So you don't know how they align to each other. It's not easy to see. To align them, you need some kind of metric and so forth. There's certainly a lot of underlying structure to them that you should exploit. And you might have actually pieces of this sequence missing. So some protein domain corresponding to a piece of this sequence would be missing, and still you would have to be able to classify that appropriately. Okay, so there are really, as far as I see it, two main approaches to dealing with this representation problem. One is modeling. That is, we construct a density model over these examples, and then how we estimate that density model then has to be connected to the discrimination task. The other one is method by which we induce alternative representations for these sequences that are more feasible in the context of classical discriminative methods. So I would like to use an HMM to derive a representation that I can use in a standard classification method, and show that that indeed is a sensible thing to do. Okay, so just to highlight the point about a discriminative generative aspect, let's suppose we have a two-class classification problem, but we have a very poor class of models, which is a single Gaussian model that has to be the same for both classes. Okay? So So this is a very naive example, but the underlying idea is actually true for almost any modeling application. So what would a generative model do if we try to estimate that model to model the density of the examples? Then it would find a Gaussian something like this, okay? So now if I'm allowed to adjust this Gaussian to improve discrimination rather than modeling the examples, then one choice of that Gaussian is to model only examples from one class, and consequently I would actually be able to classify these examples correctly, perfectly, with the same poor model. So this is just a simple example to show that when you adjust your poor density model towards classification, then you can actually improve quite dramatically their classification performance. Okay, here's another example about anomaly detection. So here we have a class of examples from only one class. We train that simple Gaussian again over these examples, and the resulting Gaussian would look something like this. So that Gaussian does not capture the class of examples. It only basically is geared towards where most of the examples are. Okay? A discriminative approach to this problem will try to capture the regularities in this class so that you have tightly capture the essence of this class. And if now we are given a new example to classify whether it belongs to the same class, then this discriminative decision boundary would be more effective in that classification task than the standard density model. Yes?
I'm a little confused by this example because you don't show two classes in this case.
That's right. So the setting here is that you, say, take a protein sequence, then there are sort of tons of proteins that fold in various ways. And if you are just looking at a particular family of protein sequences, and you want to sort of create a model that would be effective in separating that family from everything else, then it's very hard actually to find a representative sample of negative examples from that class. And even if you could find it, then just by sparsity arguments, then you might actually twist your classification boundary somewhere that you wouldn't want it to be. Yes?
It's not clear to me that the discriminative model that you have here is necessarily better at anomaly detection than the one on the left, because it might very well be that the one on the right will just give you a bunch of false negatives in the sense it will say that anomalies are normal.
So you're saying that these would really be outliers?
Right.
And yes, you can actually, this is...
You can't argue that one is better than the other.
Right, so what I'm claiming here is that there are a set of examples that basically define the class, okay? And that those may not be just the most typical examples. And so if you are better trying to account for how you can adjust the model for the set of examples, then you get a better discriminative performance out of that.
Depending on where the anomalies are there.
Right, certainly depends, right. But in general, and you can, so in many cases, this actually gives you quite a bit of improvement when you do it in a discriminative way. In fact, this is doing it the right way as far as the definition of a discriminative method is concerned. And I'll get to that later in the talk.
How can you talk about discriminative method when you don't have at least two of these? Because, I mean, if you put two, then I'm going to ask you why two and not 3 and not n, just to the next problem.
Okay, so this curve here basically defines the decision boundary that I would use based on that model to classify a new example into this class or outside this class. Okay? So what a discriminative method does is it optimizes that decision boundary. Right. Not necessarily everything. You can deal with outliers in this context as well, but yeah, it tries to capture the class as a whole more than generative approach. We can certainly talk more about this later. So really what I'm going to talk about is a little bit about the representation for discrimination, then starting to develop the formalism based on regularization theory, leading to maximum entropy discrimination that can sort of accommodate all these various forms of discrimination tasks that we would like to solve. And here are the generalizations that we can expect from this. We can estimate the structure discriminatively as well as the parameters, deal with incomplete labels, feature selection, anomaly detection, and so forth. Okay, so the list is certainly not complete, but as far as our research is concerned, this is where we are currently. Okay, so about the representations. Here's, again, one of those sequences, protein sequences, sequence of letters, and we can certainly imagine estimating a hidden Markov model over such sequences. They're variable length, so that's no problem with hidden Markov models. And suppose we have some reference model, hidden Markov model or other, for the other class, not for this family of sequences, then any new sequence that we get would be classified based on the sign of this log likelihood ratio. Okay, is this sort of clear to everybody? That if the models were perfect, then this would in fact be the optimal decision criterion to classify the sequences with. Okay, so now a typical way of viewing this is to say that let's fix the parameters and see how different examples fall into different sites of 0, so have different sign, and therefore we have a decision rule. Okay? In terms of representation, we want to view this differently. Let's fix the example and see how this decision rule varies as we vary the parameters. So an intuitive way of thinking about it is that when you're classifying an example, you look at how, say, 10 different classifiers would classify the same example and use that vector now as a representation for the example. Okay, so a little bit more formally, the example will be mapped into a set of discriminant functions when we vary the parameters of our HMM. So each parameter gives us a particular value, how that HMM with those parameters would classify this example. And now we use a set of those as a representation for this example. So it's using the model class as a whole rather than a model with a single parameter setting. Okay, and in fact you can show that this representation will always improve the classification of your model. Or with this representation and standard linear classifier, I can improve the classification of your model, assuming your model wasn't perfect. So this representation contains more information than the likelihood value that you can get, say, out of HMM. Okay, and here's a sort of an experimental demonstration of that. This is a large-scale problem in classifying protein sequences into different families. The red dashed line here corresponds to state-of-the-art HMM models that people have used in this context. And the blue line is when you use this representation, combine those representations with standard discriminative methods such as subword vector machines, and you get a considerable improvement in the classification accuracy. So what this should tell you is that the HMM models that we used for protein sequences are far from perfect, because it's very easy to considerably improve them using these representations. Okay, so that type of representations for examples actually arise fairly naturally from a more general discriminative framework, the maximum entropy framework that I will develop. But before doing that, I have to back up a little bit and start from sort of simple regularization approach and show how a series of generalizations of that regularization approach lead to something where we can solve a large class of these problems that we're interested in solving. Okay, so to define a regularization approach, you have to do two things. You have to define what is the discriminative function that you're using. In the previous example, it was the log likelihood ratio of two, say, hidden Markov models. And for simplicity, let's say it's linear in this case. Okay, so the sign of this linear combination of the components of X now give me the classification rule. Okay? Then we want to estimate parameters so as to separate the training examples maximally. Okay? So if you aren't familiar with sort of large margin classification, with what this is trying to do, then I can give you possibly if you're familiar with information theory, then there's a sort of a motivation for large margin classification, and it's the following. Any endpoints I can map onto, say, log n dimensional space with some distortions between the pairwise distances of these examples. Okay? So lower the dimensionality of the space, the fewer examples I need for linear classifier to give me a good performance. Okay? So now if I have a large margin classifier, then I can distort the pairwise distances quite a bit and map the examples into a very low dimensional space, and still the same classifier would be would have zero error rate. So that's actually a way of analyzing how well large margin classifiers might perform. Yes?
If you're going to tell us later, don't answer now, but how would you pick the dimensionality of the lower dimensional space?
Okay, the funny thing is that random projections will do the trick. Just take random projections, roughly to log and dimensional space, and you'll have that property. Yes?
Once you find the optimal, separation, and you've mapped it to this lower dimensional space, and you've trained everything, you have everything done, and now I give you a new example, right?
Right.
And that example, is exactly the type of example that is hard to do. In other words, maps somewhere in the middle of that, exactly
right.
at the point where you have collapsed, to some random thing that
right.
you don't know what is going to happen. So I guess what I'm trying to say is that you seem to be, fudging the area exactly the area that is I guess most important.
But here I'm assuming that there is a margin. I'm classifying all the training examples correctly with a large margin. And if I now allow only a certain level of distortions between the pairwise distances of these examples, then I still retain that all the examples, at least the training examples, are mapped onto the right side.
Okay, but you're not going to use this distortion when you actually, classify a new sample.
Right. So this is a way of sort of conceptualizing why maximum marginal classification is good.
Okay.
Because effectively you are working with a lower dimensional problem. Okay, so just for future reference, let's map this problem into a different form. So we have some regularization penalty that we are minimizing, subject to classifying all the training examples correctly. So when the sign of the training example is the same as the sign of the discriminative function, then this is large and positive, and we want to make it large and positive as far as we can. So this is a large margin sort of formulation for classification method. And C here is a penalty for sort of setting this too close to zero or even negative. Is this sort of clear? what this formulation does? Okay, so a couple of problems with this formulation and things that I would want you to keep in mind. How do we choose the regularization penalty here? It's not clear. And why do we use a point estimate for the parameters here, rather than, say, use a wider distribution of the parameters? So in fact, it is typically the case that there are a large number of nearly optimal solutions to any classification problem. Okay? Which one of the solutions you picked is not clear. But what you can do is actually use a collection of them. Collection of parameter values that give you a good classification performance. And by doing so, in fact, you are making a coarse description of the identity of the parameters. So you fudge where the distance boundary actually has to lie when you have a large number of near optimal solutions, and you encode that probabilistically. So effectively what you're doing is introducing a distribution over the parameters. And then when you are classifying, you simply average the discriminating function with respect to that distribution. And that is now your new discriminating function. Okay, so now this problem of finding a parameter setting is transformed into a problem of finding a distribution over the parameters. Yes?
Once you have the distribution over the parameters, how do you average the models? Do you do like Monte Carlo estimation?
Right, so I'm assuming here that I can do it exactly. So there are certainly issues in whether I can do it exactly or not. And we can talk about that later on. Okay, so what I have to do now to cast this as a regularization approach is to find an appropriate way of regularizing the distributions over the parameters. And in fact, there's a simple information theoretic argument what that regularization should be. Okay? So let's say we have some prior distribution over the parameters, maybe flat. We don't know anything about which parameter values would give good classifiers. After observations, if we look at any distribution that classifies, allows us to classify the examples correctly, it's different from the prior. And now you can compute the information that has transferred from the training examples to the parameters or distributions over the parameters. And that information is the KL divergence in this way from the new distribution to the prior distribution over the parameters. So just intuitively, you're trying to minimize the number of bits to extract from the training examples and still maintain the same level of classification performance. The minimum number of bits, if you minimize that, then you're guaranteeing that you generalize better to any future examples, because you needed less information from the existing training set to classify them correctly. Okay, so this suggests a sort of uniform regularization penalty for the distributions, which is the KL divergence. So here I have now new regularization penalties completely in terms of KL divergences, so minimizing the number of bits extracted from the training set, same classification constraints, but now averaged over these distributions. So this is a weaker condition than saying that it has to hold for a particular parameter value. It has to hold only on average. Okay, that is what I gain by looking at distributions over the parameters rather than a fixed value. Yes?
So P of theta subs is really, theta is a model parameters. So these are the distribution of the model parameters.
Right. That's correct. And so now this is a regularization approach, not in terms of the original parameters, but in terms of distributions over the original parameters. And we classify any new example by averaging with respect to whatever distribution this method gives us. Okay, so what this, there's no need to understand all the details, but what it actually gives you is a sparse and unique solution. Sparse because if you impose some of these constraints, then the subsequent constraints are satisfied by virtue of having imposed them for a few examples.
I think, what was P guarantee?
Okay, so so this is actually a little more general than I'm presenting it now for clarity, but you can assign a distribution over the margin as well. So you don't know what is the value of the margin that you can retain for any particular example. So you have some uncertainty about that as well. And you deal with that uncertainty like you deal with the uncertainty in the parameters in a sort of uniform way. Yes?
Also, do you assume that the structure of the model is correct?
Do I assume what?
Structure of the model is
Structure of the model is correct? No. There's no assumption. Plot any discriminant function here, then the formalism works just fine. But obviously, if the structure is correct, then this will lead to a far better classifier. And it is really important to have the structure correct, since this involves sort of the model class, not just a particular parameter setting. So effectively, what the model gives me is the structure, how examples are structured. Okay, so another thing that this gives you is the choice of the penalties for the margin. They come from the same information theoretic argument. And then you can assign whatever priors over the margin and the parameters that you wish.
Question.
Yes.
So why is it sparse?
Why is it sparse? Because for the same reason as, say, the regularization theoretic approach gives you a sparse solution. So if you impose these constraints for few training examples, then the remaining constraints may already be satisfied. Does that make sense? Okay, I'm not sure if I should, how much time do I have actually?
Like 5:30 is the clock for the telecom.
Okay. Maybe I should
25 minutes.
just hurry up a little bit. So this is just to say that casting the regularization theory or generalizing that into specific distributions allows you to view this algorithm as a projection method, that you're projecting from whatever prior knowledge you have to the admissible set, that is the set that allows you to classify the examples correctly. So a set of distributions that would lead to, or would satisfy those constraints for training examples. Okay, just one point about the form. There's a general form, like in any maximum entropy estimation problem. For the solution, it is the prior times some exponential form where you have Lagrange multipliers associated with the constraints, classification constraints, and then the constraint. Okay, so the reason why I'm bringing this up is that in order for this method to be feasible, you have to be able to normalize this distribution. Okay, so that is the crucial thing. If you can normalize it, you can use this methodology directly. And that is the point where this may or may not be computationally feasible. Okay, so this basically is the end of sort of their formal development, and then I'm going to show you how we can address the problems that I posed earlier, the various generalizations within that same framework. But just in relation to other methods, so me and David Hausler proposed a new framework for classifying protein sequences based on something called Fisher kernel, and this sort of pops out from this more general discriminative framework. If you've heard of super vector machines, then they can be obtained from this framework by appropriate choice of the discriminant function and the prior that you have. It's also related to boosting and multiplicative updating training algorithms. Any sort of questions about the basic framework before I get into the generalizations? Okay, so let me actually do this fairly quickly. So since you're dealing with distributions over parameters, there's really no difference between whether the parameters were discrete or continuous. So the discrete parameters would encode the structure of the model, and continuous parameters would be the usual ones. So you can certainly see that we can deal with structure estimation problem discriminatively within this framework as well. So the big question really is not that, but whether this is feasible at all. So estimating the structure of any graph model is super exponentially hard, so it's not that easy to do. And it turns out that this is tractable when your graph models have a tree structure. So in this context, you can actually represent and deal with distributions over structures and estimate them discriminatively within this maximum entropy formalism. It all sort of boils down to a simple generalization of well-known matrix tree theorem. Okay, so more interesting generalizations. Now, if we have large number of unlabeled examples and only a few labeled examples, then we would like to derive a classifier that's better because it exploits the unlabeled examples. Okay? Before doing that, we should think about why would we even expect unlabeled examples to benefit at all in a discriminative setting. So if we are only interested in about the conditional relation between example and the label, and if the label is missing, then what possible information I have from the unlabeled examples? Now it turns out that the information that I have is my bias towards maximum margin classification. Okay, so if I try to relabel the unlabeled examples, then some of those relabelings would give me larger margins for the eventual classifier. Okay? So if I favor large margin classification, then I will favor those type of labelings that allow me to classify all the examples with a large margin. So there is an inherent bias in this framework that you can exploit. So in terms of regularization theory, the unlabeled examples serve to regulate the type of classifiers that I'm inducing. And then whatever that set is after the regularization, I will pick from that set the one that's most consistent with the labeled examples. So let me say that in pictures. So let's say these are three sets of unlabeled examples. Okay? So now there are three favored solutions to this problem, favored in terms of this large margin bias. These three, if you can see them. Okay? So without seeing any labeled examples, the classifier would favor, say, that these three solutions are the most likely ones. And when we actually do get a few labeled examples here, then we can choose, essentially, choose out of these selected ones, the one that's most consistent with the labels. So hopefully this tells you that this maximum margin approach actually can exploit the unlabeled examples. So if the unlabeled examples are clustered in a way that the clustering corresponds to the label that I want to, or the actual underlying label for that example, then this bias is the appropriate one. That using this bias actually improves classification performance, yes.
So how do you find this application? How do you find it?
You can, well, let me actually get to that a little bit later. I have slides for that, yes.
I was wondering whether you really care what label you put in any of those, or you care whether, so long there, you get groups together.
Right, so I actually don't care how these are labeled, but I care how they constrain my classification boundaries.
Right.
Yes. Yeah.
How do you know that the labels, or how do you ensure that the labels in a single cluster belong to a single class?
I don't know that. So I can certainly imagine situations where unlabeled examples cannot possibly help you at all. So if they are they are distributed uniformly, and then I just, the true classifier is just a line between, and I give you a few samples from each side of the line. And there's no information in the unlabeled examples. So the hope here is that the natural problems actually are, the natural data is clustered in a way that examples that have the same label correspond to the same clusters. And in fact, when you apply this to natural problems, that's what you find. You can actually exploit this, yes.
So in the maximum likelihood way of doing things, are you saying that if I had labeled data, I would estimate class conditional densities, and what the tons and tons of unlabeled data does is it can't tell you any individual class conditional density, but it tells you what their mixture looks like. Because after all, these are all, what you see without the label is a mixture of those densities.
Right, yes.
And that's why number 3 is better, because it separates those.
Right. So effectively, this method is doing clustering of the examples, but not in the usual way, because the family of discriminant functions that I use actually determine the type of clusterings that I allow. Okay, so just a little bit more formally, no need to understand the details, but just that there are two things going on here. One is the regularization bias that comes from the unlabeled examples. So I can express them as constraints of this form, where I'm now also averaging over the uncertainty about the labels. So in this approach, you average over all quantities that you're uncertain about. And then once we have that regularization bias, then we include the constraints corresponding to the labeled examples. And then the solution to the whole thing is what allows us to exploit unlabeled examples. Okay, and there was a question whether, let me skip this. You can show in simple cases that this has the right bias. The regularization bias, the maximum margin is the right one. But typically, this gives you a very difficult problem to solve. And to solve this efficiently, you can actually resort to a very natural approach, which is saying to say that you no longer search for distributions, maximum entropy distributions, in the space of all possible distributions, but in some class of distributions that you can deal with efficiently. Yes?
Question. So I don't understand. So what is YT if T is unlabeled?
YT is a variable that can take two values, plus minus 1, and there is now a distribution over that. So you can assign you have to assign a prior distribution over that. If you have no idea, you can say 0.5, 0.5, and then just include that in this average. And what you will find is then the maximum entropy distribution over those labels as a result of applying this algorithm. Okay, so the way you deal with the computational issue is to impose additional constraints now on the form of the distributions that you're searching for the solution. Okay, and obvious question is whether it works at all, whether it just looks intuitively correct, maybe. So here's a simple example to show that you can actually, at least sometimes, get most of the benefit from unlabeled examples without having any, or 90% of them missing. So this is a simple classification problem for DNA sequences. And the black line here is when I only have a small set of labeled examples, and I can use only those to estimate a classifier, and this gives me an ROC curve corresponding to that classifier. Yes?
So what does it look like after below 10%, like 5% labeled, 1% labeled? And totally unlabeled?
Actually, so this gap would get a little bit wider. This red line would also sort of fall away from the true or the best possible thing that you can do. But it is still better than, at some point, it of course breaks down. If you have no labeled examples, and
no, but the question is, in a case, it might be, depending on the problem, there are problems where even if you have a completely unlabeled example, you can still do a good job because data naturally clusters.
So what you get in that case is the right bias. So let's suppose we have a very simple case where we have two Gaussian clusters, and I don't know which cluster corresponds to which label. Okay, this method would actually find the correct decision boundary, but would be unclear about how to flip the signs across the boundary. And so it would actually predict 0 for the label, since it doesn't know both interpretations are equally likely. But given now one labeled example, it would get the boundary correct. But without any labeled examples, you really don't have.
I guess the question I still is trying to get at is what would be the performance if you had only one labeled sample in this case?
In this case, okay, I don't know.
That's the essential difficulty of this classification process.
Right.
The other question would be, suppose you built a maximum likelihood classifier on your 10% labeled data, and then labeled the remaining 90%, and then retrains. Where would that fall?
So basically, people have used sort of an EM approach with models to deal with unlabeled examples. And this is sort of a purely discriminative way of dealing with unlabeled or exploiting unlabeled examples. And so the problems with the EM is that you don't know when it diverges. So sometimes the unlabeled examples completely overwhelm the solution that you actually don't pay any attention to the labeled examples because there are such a large number of unlabeled examples. And your poor model just tries to capture the density, not really the class conditional distributions. So it certainly, in some cases, would perform okay, but there are sort of theoretical problems at this point in understanding when it works and when it doesn't. I'm actually working on that very question, so I'm not claiming that that approach is not useful at all, but it is certainly open at this point. Okay, so I guess I don't have much time, so I'll just run through a feature.
Chris, we have until 6, but 1:45.
Okay. Well, I can stop after feature selection. If you want me to continue, then that's fine. So it'll be up to you. Okay, so another way of generalizing this approach is to do feature selection. Features, the actual selection of features is sort of unknown to us. What are the features that are most important for this classification task? And we would like to determine what features are most discriminative in the process of training the discriminative method. So there are essentially two approaches to feature selection. One is a filtering approach where you basically try to determine what the important features are, regardless of the type of classification method that you will use in that problem afterwards. And I would argue that when you do it jointly, you can actually exploit more or get the features that are appropriate for the type of classifier that you are using. So there's a sort of performance benefit for doing it jointly. There is certainly a computational disadvantage for doing it jointly rather than separately. Okay, so let's take a simple example. We have a linear discriminant boundary, and we now introduce selection variables that are 0 or 1, depending on whether we pick that component of the input vector or not. Okay, so what is the effect of those selection variables? So effectively what happens is the following. So if this value of the parameter gets very small, then at some point this method will switch that component off. And so effective weight for small values of the weights goes to 0 very quickly. So without any feature selection, the weights that are small would continue to be small, not sort of adversely pushed down. But based on this selection, you sort of push down everything that appears to be irrelevant. And the location of where the switch happens depends essentially on your prior belief about how frequently these features are really on or off.
It almost seems counterintuitive to the regularization approach, where you want to penalize large things, right? I mean,
yes, this is all in the context of the same regularization approach. I'm just showing that you can have a single methodology and apply it in various ways to various different problems and get sort of this state-of-the-art solution. Okay, so how well does this work? Here's, again, a simple example where we have 100-dimensional input vectors. And the red line here corresponds to the ROC curve of a method that does not use feature selection. And blue line is when you apply this feature selection. So feature selection in this context is not just for computational benefit, it is for the benefit, actually to benefit the performance of the classifier. Okay, so perhaps one counterintuitive feature of this is that when I get more and more examples, this gap closes. And if I have only very few examples, then the gap is very large. So feature selection works best when I have only few training examples. You can motivate that on the basis of sort of dimensionality of the problem. Feature selection reduces the dimensionality of the problem when you have very few examples, and the resulting classifier you can estimate more accurately on the basis of that. And you can sort of expand this or handle this very fairly efficiently, even if you have thousands of features, and get similar level of performance increase as a result. Okay, so I can either stop now or go through anomaly detection. Okay, so so the last type of generalization is anomaly detection, where we have examples from only one class. And we want to estimate a decision boundary on the basis of those examples that would allow us to discriminate those examples from diverse set of other examples. Okay, and the motivation here is the following. If now I resort to the standard approach and estimate a model over these examples that I have, and then threshold the likelihood value when I see a new example, and if it's above the threshold, I'll include it in this class, otherwise not. Okay, so you are using an effective decision boundary in that context. The boundary is the log probability of the example given the model, and then some threshold value. Okay, so this is a discrimination problem. And now you can optimize the parameters of this model to optimize this decision boundary rather than the likelihood of the examples. And that is, again, in line with the original goal of doing exactly, in the estimation process, doing exactly what you're doing when you're evaluating the method. Okay, so...
Isn't that a form of likelihood estimation, though? I mean, you say that your model is, you sort of cut it off if it drops below gamma.
Well, think of it this way. If there is an example for which the probability is already higher than my threshold, then I'll ignore them completely. I don't use them in the estimation process subsequently.
Negative in the likelihood of them is negative infinity, so you don't even consider that model, right?
Sorry, what do you mean negative infinity? So let's say there's an example that's highly likely, so one of the very typical examples, okay? Then that certainly should be above my threshold, right? Okay? So those examples, for those examples, these constraints are satisfied automatically. And I don't have to include them in the estimation process. So you can view this as a way of estimating a model from the examples when I'm sort of weighting the examples in a funny way or ignoring them completely.
Or insisting that your model assigns some minimum probability on it. I don't want to dwell on it. You've got constraints which you can push into the model and then treat it as maximum likelihood.
Yes. If it's false, you can sort of approximate this by, say, setting a certain threshold and then going through your training set, whatever is below the threshold, use for estimating the model, and then redo this and sort of iterate. And it would approximately do something that I'm proposing here, but not exactly. Okay, so as a result, we can formalize this in the same way as we have before. We average over the distributions over the parameters and the margin values and minimize some regularization penalty coming from the information theory criteria. Okay, so now what happens in this solution is that the solution is constructed on the basis of only a few of the data points, the relevant data points, rather than concentrating on the points that happen to be most frequent. Okay, so the following thing happens as a result. If I now look at the log likelihood of the examples that standard Bayesian method of estimating this model would give me, and what this discriminative anomaly detection method would give me. So there's one major difference. The Bayesian approach gives me a very broad distribution of likelihoods over the training examples. This anomaly detection method gives me a very sharp distribution. So ideally, all the examples would have the same log likelihood. Which is, in a way, this is constructing an equivalence class over the examples, where the equivalence class is determined by the likelihood value. Okay, and you can show that when you do this anomaly detection method discriminatively, then you get sizable performance increase as a result. Coming mainly from the fact that evaluation criterion now matches the criterion that I'm training this way. So, just to summarize, I've proposed a general framework for dealing with discriminative estimation problems and you can generalize that framework very naturally to a large class of problems of interest in several different fields, including information retrieval and computational biology. And this list keeps increasing. So sometimes this methodology is not feasible, but in many cases there are feasible approximation methods that you can use. Okay, sorry for going a little over time. That's about it.
Questions?
There are questions.
So, so how do you estimate over the model parameters for an HMM?
How do I estimate if I wanted to do this for HMMs?
Yeah.
So one way of doing it is to say, first train the HMM and find the maximum likelihood parameter setting. Okay? That defines some point in the parameter space. Then I look at some small region around that. That is, I'm trying to perturb the model in a way that would gear it more towards discrimination. And that you can do efficiently even with HMMs. And in fact, the protein homology results that I showed you were in fact using this very method. And you get a considerable increase in the performance by just perturbing the model locally and training that discriminatively. Yeah.
You assume perfect separability?
No. So the question that I sort of tried to avoid during this talk is to talk about the margin and the fact that I'm also assuming a distribution of the margin values, and you can treat that margin parameter now as an uncertain quantity in the same way as in the original regularization framework. But it's sort of the intuition for that is perhaps a little more complicated. That's why I didn't want to touch that.
I had one question on the slide just before the last one. The likelihood comparisons that you show, is it because your discriminant model is essentially a large mixture? Isn't it because you're averaging over all thetas and gammas? So the blue likelihood curve is essentially the likelihood assigned by a mixture model. Is that why it is so much higher? Because after all, it in some sense is an infinite number of modes that it could mix.
That is not the reason in this context, but it certainly that aspect contributes for it to be sharper. But the reason why it is sharper is that you don't forget example, because maximum likelihoods basically forgets a lot of examples. That allows you to have a very low likelihood for some of the training examples, so long as you capture the main mode correctly. So what this does is to concentrate more on the examples that are harder to capture, and therefore everything sort of looks more similar because you didn't train much more the more frequent examples, or you don't get a higher likelihood for those.
You're concentrating on the margin.
Sorry?
You're concentrating on the margin.
Okay, let me give you an intuitive way of seeing this. If I start pushing these examples here, to make these unlikely examples based on the standard way of estimating towards 0, I cannot certainly push them past 0 because not all examples can be explained by the model with probability 1. So at some point, this has to become sharper, and you have to give up from capturing some of the likely examples. So it's just an intuitive picture, but the more formal justification for that comes from the fact that you threshold. So you don't train examples that are already well captured by the model. And therefore, you drop essentially this pattern at the expense of moving this closer. Yes?
What is the performance when the number of classes increase? Do you have any study
Um,
into that? So two class, I don't.
Right, so this is, basically I showed this for two-class case. You can extend it fairly naturally to multi-class, like logistic regression versus softmax regression. In the same way you can extend this to multi-class. There's a far more interesting approach nowadays for multi-class classification coming from error-correcting codes. That essentially you use binary classifiers, a sequence of outputs from binary classifiers to construct an efficient code for the multiple classes that you have.
Any other questions?